Hello, this is the start of lesson 25 on the weak law of large numbers. First, we're going to do a little recap of the central limit theorem with an example. Let's say we roll 10 dice and we want to find the probability that the sum of the 10 values is between 30 and 40. The expected value on a single roll of a standard die is 3.5. Variance is 35 over 12. Just a brief recap here of finding the variance, expected value of x squared, summation x squared times p of x. A fair die probability is uniform at 1/6 times the sum of x squared, and you can add those up or use the formula for a sum of squares. And the expected value of x squared is 91 over 6 minus the mean squared gives us the 35 over 12. Now, applying this to the sum, we have that the mean will be n times the individual mean, which is 10 times 3.5, 35. Variance, again, also additive, so it's n times the variance. It's going to be 10 times 35 over 12, and then you would take the square root for the standard deviation. Now, rolling a die, the outcomes are discrete there 1, 2, 3, 4, 5, 6. But we're shifting over here to a normal distribution, which is continuous. So technically, we should be doing the continuity correction, which is to add or subtract 0.5 on the endpoints essentially here. So since these values were included, since it was 30 to 40 inclusive with the equal signs here, we're going to go expand outward, down a half on the 30, up a half on the 40, and work with 29.5 to 40.5. And then we have to convert each of those to z-scores. Now, we actually make the small correction here. We're looking for the total to be between 29.5 and 40.5. All right, so we have to convert these over to z-scores. We're going to do each of these values minus the mean of the total divided by the standard deviation. So it's going to be 29.5 minus 10 times 3.5 divided by sigma times root n. So we're using the mean for the total, which is n times mu, and then the standard deviation, which is root n times sigma squared, or sigma times root n. We get 5 point, this should be a negative number here, 29.5 minus 35, so it's negative 5.5 over 5.4, it's negative 102. And when you do the 40.5, you get positive 102 because 29 and a half and 40 and a half are equidistant from the mean of 35, so we just have opposite signs there. And then putting this into the looking this up on the Z chart, you'll get a probability of 0.692. So about 69.2% chance that the sum for 10 rolls will fall between 30 and 40. All right, up next, weak law of large numbers. Suppose we have n independent, identically distributed random variables. The probability that the mean of these n variables minus the individual mean, population mean, greater than or equal to epsilon, that probability goes to 0 as n goes to infinity. So we're given that the n random variables are independent, identically distributive. They have the same distribution, so they have the same mean, standard deviation. Each one has a mean of mu and a standard deviation sigma. Now it's a little bit different here. We're dealing with the mean instead of the total, but it's the same idea. So we have to, if we want to find the mean of the mean, essentially here, x1 plus x2 up to xn over n, the expected value of that is going to be 1 over n times the expected value of the sum, which we know is n times mu, so the n's cancel out, and we end up with a matching mean. So the expected value of y is equal to the expected value of x sub I, which is just mu. Now the variance, by properties of the variance here, the 1 over n comes out as 1 over n squared. So that factors out as 1 over n squared, and then since the variables are independent, we can add up the variances, so it's n sigma squared over n squared, or sigma squared over n. So again, for this calculation, which is the mean of n independent, identically distributed random variables, the expected value is the same. The variance is a little bit different. It's sigma squared divided by n. So just a brief recap of those rules. Expected value of a times x, the a factors out. So the 1 over n factors out. For variance, it factors out as a squared. So 1 over n factors out, becomes 1 over n squared. So the variance is sigma squared over n. The standard deviation is the root of that, so it's the root of sigma squared over n, which is sigma over root n. All right, so we want to fit this into Chebyshev's inequality here, which is true for any distribution. So we have from Chebyshev that the probability that absolute x minus mu greater than or equal to k times sigma is less than or equal to 1 over k squared. Now we want to fit this into our format here, which is looking at the probability that x1 plus x2 up to xn over n minus mu greater than or equal to epsilon. So what we want to do is get the standard deviation involved here. And so we're going to multiply top and bottom by sigma y. And this should be a y here, because that's the mean. And so we're looking at the probability that absolute y minus mu is greater than or equal to epsilon times sigma y over sigma y. So what's happening here is that epsilon over sigma y is taking the role of the k in Chebyshev's inequality. So this expression here is our coefficient of the standard deviation. So that's our k. And then it gets in the denominator squared on the other side here. So that's where we get less than or equal to 1 over quantity epsilon over sigma y squared. So that flips over to sigma squared y over epsilon squared. Now remember, sigma squared is sigma y squared is sigma squared over n. And what's going to happen is, as n goes to infinity, these other terms are fixed constants. That expression will go to 0, and we will get the result that we wanted here. So a little bit of technical detail here, kind of a redo. Basically, epsilon is k times sigma over root n. It's k times sigma y. Here we just have a specific example that if you want to know the probability of being more than 2 standard deviations away from the mean, so the probability of being more than 2 standard deviations away from the mean is less than or equal to 1 over k squared 1/4. So it's at most 25%. Now we want this epsilon to be in that format, so we're defining it to be k times sigma over root n, or k times sigma y, so it fits the form. Yeah, so epsilon is equal to k times sigma y. If you divide by sigma y, we get k is equal to epsilon over sigma y, which is what we have in this format here. So 2 different ways to arrive at that point. Now sigma y is sigma over root n, and so basically we flip that over, and so we get epsilon times root n over sigma is in the denominator squared, and again, that flips over upside down, so we do end up in the same spot. Sigma squared over epsilon squared times n. So again, 2 different ways to arrive there. You certainly don't have to do it both ways, but hopefully it provides some insight into this procedure. So the idea here is that as n gets large, this expression is of the form a constant over infinity, and so that will go to 0. As n goes to infinity, this expression, constant over infinity, goes to 0, which is what we were trying to show. So again, weak law of large numbers, the probability that the average of the n independent variables minus the individual mean being greater than or equal to epsilon, that probability approaches 0 as n goes to infinity.